Okay. Okay, now we can get started. Since we have everything finally working. Okay, so we left off on the derivative of an inverse function. All right, so let's just do another example to kind of act as a refresher. Okay. So what if we want to find the inverse derivative at some value a for f of x is equal to the fourth root of negative x minus 4 when a is equal to 1. And this is just Newton's long-winded way of saying find f inverse prime of 1. Okay. So if we're looking for our f inverse prime of 1, first thing we have to do is find the f inverse of 1. And honestly, we can just make f inverse of 1 equal some unknown x. Now we have to solve for x for our function. So f of x is equal to the fourth root of negative x minus 4. Now, if f inverse of x equals x, we're going to apply the function f on both sides. So we have, let me move that over a little bit, make sure I don't run out of room. And get my eraser out. There we go. So the function f of f inverse of 1 equals the function of x. Okay, so we know the function and its inverse cancel each other out, leaving just the argument, in this case 1. So we have f of x is equal to 1. So we have f of x is equal to the fourth root of negative x minus 4, and we know that f of x is equal to 1. And we can just combine those two and say the fourth root of negative x minus 4 is equal to 1. Okay, so now we can solve for x. We just have to raise both sides to the fourth power to get rid of that fourth root. So that fourth root of negative x minus 4 to the fourth power is equal to 1 to the fourth power. Okay. Well, we know the exponent and the index cancel each other out, leaving just the radicand negative x minus 4. equals 1 to the 4th power, which is still 1. Okay. So if we go ahead and add 4 to both sides, those two cancel each other out. And we are left with negative x is equal to 5. Well, we don't want negative x, we want the value of x. So we just either multiply or divide both sides by -1. Doesn't matter because they both give you the same answer. Negative ones cancel each other out. So we know that x is equal to -5. Okay, so the same way we were able to kind of combine the f of x, having a different value, well, not different value, but a value and a function, we can do the same thing with f inverse of x. So we know that since f inverse of 1 is equal to x, and x is equal to -5, and you can flip those around if you want to, x equals f inverse of 1, and x is equal to -5, you can just set those equal to each other. We close that up. We know that f inverse of 1 is equal to -5. Okay, so this is where we start plugging it into our formula. So we know the derivative of an inverse function is f inverse prime of x is equal to 1 over f prime of f inverse of x. Okay. What we're looking for, the inverse derivative, bring that down, the inverse derivative at 1. So f inverse prime at 1 is equal to 1 over f prime of f inverse at 1. Okay, so this part right here, we can use that to replace this part right here, that f inverse at x is equal to 1, or a is equal to 1. Okay, so we can rewrite it as f inverse prime at 1 is equal to 1 over f prime, and that f inverse at 1, we just replace that with -5. Okay, so now we just have to find f prime of -5, which we can do that right over here. And yep, that's it. So that f of x is equal to the 4th root of -x minus 4. We can just rewrite that as -x minus 4 to the 1/4 power, since it's the same thing. So using the chain rule, you know that f prime of x is equal to, we get that 1/4, bring it down to the front, -x minus 4 to the 1/4 power minus 1. Give that a little bit more room. 4 minus 1 times the derivative of what's inside. negative x minus 4. Make that a little clearer. Okay, so that gives us f prime of x is equal to 1/4 times negative x minus 4 to the power of 1/4 minus 1. So that's 1/4 minus 4/4, which is negative 3/4, times the derivative of negative x minus 4. So the derivative of negative x, well, the derivative of x is just 1, so negative 1 times 1 is negative 1, minus the derivative of 4. Well, we know the derivative of a constant is always going to be 0, so that's just 0. So we can just drop that one. Okay, so that negative 1, we can go ahead and multiply negative 1 times 1/4. But we're looking for f prime of x to the, well, of negative 5, f prime of negative 5. So if we have f prime of negative 5, that's just negative 1/4 times negative 5 minus 4. So negative 5 minus 4 to the negative 3/4 power. Well, negative 5 is just positive 5. So positive 5 minus 4 is just 1. So 1 to the any power is just going to be 1. So you have negative 1/4 times 1 is just 1. So f prime of negative 5 is just equal to 1/4, negative 1/4. Bring the camera down just a little bit. There we go. So this f prime of negative 5, we can replace that with negative 1/4. That's equal to 1 over negative 1/4. Well, that form is a little bit messy. So that negative, we can just factor that out to the front. But to simplify this, let me bring that down so it has a little more room. Won't look so messy. 1 over negative 1/4. So we just multiply the numerator and denominator by the reciprocal, which is 4 over 1, or just 4. So that negative just goes out to the front. This 1 over 4 and 4 cancel each other out, so we're left with just negative 4, which is our f inverse prime at 1. Make that a little neater. That still looked a little messy. There we go. All right. Are there any questions on that one? All right. Okay. All right. Anyone still writing? All right. Okay. So let's say with this one, and every once in a while they'll throw a concept question at you just to see if you know what you're doing. What if we wanted to find f inverse prime at x is equal to 4, you're given the table. And so you have your x, your f of x, and your f prime of x. Okay. So let's say we know that x is equal to -3. F of x is equal to 4, or basically f of -3 is equal to 4. And f prime of -3 is equal to -2. Oh, why did I put a parenthesis there? Okay. So again, this is just kind of their way of testing your understanding of the concept. So we're going to start here. We know that f of x is equal to 4. Okay. Well, we know if f of x is equal to 4, we can just apply f inverse to both sides. So that gives us f inverse of f of x is equal to f inverse of 4. Okay. So we know again that the inverse and a function cancel each other out, leaving just the argument. And in this case, that argument is x. So we know x is equal to f inverse of 4. So once again, we're going to go up to our table, because we know that when f of x is equal to 4, we know that x is equal to -3. So if x is equal to -3 and x is equal to f inverse of 4, that means we know that f inverse of 4 is equal to -3. Okay. So once we know our f inverse value, we can go ahead, move that up a little bit, and use our formula. So we know that f inverse prime of x is equal to 1 over f prime of f inverse of x. Excuse me. Well, we're looking for f inverse prime of 4. So that means that f inverse prime of 4 is equal to 1 over f prime f inverse of 4. There we go. Well, we know that f inverse of 4 is equal to -3. So we can just take that and replace it with -3. So f inverse prime of 4 is equal to 1 over f prime of -3. Well, if we look at our table, we know that when x is equal to -3, f prime of -3 is equal to -2. So we can replace this with -2. So that gives us 1 over -2, or you can just say -1/2. All right, any questions on that one? Okay. So it's kind of the same thing, just in this case, they put it in table form. Okay, anyone still writing? Right. So now we're going to look at the derivative of inverse trig functions. Okay, so the derivative with respect to x of sine inverse of x is equal to 1 over the square root of 1 minus x squared. Okay, so instead of sine inverse of x, what if you have sine inverse of x squared plus 3x plus 5 or something like that? Or any function of x other than x? Well, if that's the case, so the derivative with respect to x of sine inverse of some function of x we'll call g of x. Move this line up a little bit. Here we go. And that's going to equal the derivative of that function divided by the square root of 1 minus that function squared. Okay. And really, you can apply this one to this one also, because the derivative of your function x is just 1. So same formula, just this one's meant for different or more expanded functions. Okay, now if we have the derivative of cosine inverse of x, it's the exact same formula as the sine inverse. The only difference is it's negative. So that's negative 1 over the square root of 1 minus x squared. Okay. Again, same thing if you have some different function of x. It's the exact same formula. Cosine inverse some function g of x. That's just equal to the negative g prime of x. And make that g a little neater. Divided by the square root of 1 minus that function g of x. squared. Okay, so what if we have the derivative of tangent inverse? Well, that's equal to 1 divided by 1 plus x squared. But if we have the derivative of tangent inverse of some function other than x, we have the derivative with respect to x of tangent inverse of some function we'll call g of x. That's just equal to the derivative of that function divided by 1 plus that function squared. And if we take the derivative of cotangent inverse, that's just the negative of that very same function or expression. But we have 1 divided by 1 plus, I have to put this as x squared. I don't know why I put the parentheses there. Sometimes it's a habit only because I changed that x to g of x. So I just put parentheses around it for some odd reason. I think just as a student, that was my reminder to change that to g of x. And the derivative of cotangent inverse of some function g of x is equal to the negative g prime of x divided by 1 plus g of x squared. Okay. So if we had the derivative of secant inverse of x, that's equal to 1 divided by the absolute value of x times the square root of x squared minus 1. And again, for functions other than x, we know that the derivative of secant inverse of some function g of x is just equal to g prime of x, or the derivative of that function, divided by the absolute value of g of x. Let me move this over just to make sure I have enough room. Here we go. So the absolute value of g of x times the square root of g of x squared minus 1. And last, we have the derivative of cosecant inverse, which is just the negative of the very same answer. So we have the absolute value of x times the square root of x squared minus 1. And the same thing with the derivative. Move that over a little bit. Of cosecant inverse of some function g of x. That's just the negative of g prime of x divided by the absolute value of g of x times the square root of g of x minus 1. Barely made it.
G of x squared now.
Oh, squared. I know. So busy worried about making it all fit. Forgot my square. Thank you.
Yeah.
So if you notice the pattern, more than just the function and their cosine being opposites, having different signs. If you notice, it's just for the sine and cosine, pretty much the same function, but cosine is negative. Same here. The only difference is they're negative. So if you can remember the regular sine inverse, tangent inverse, and secant inverse, then you can remember the other three because they're basically the exact same thing, just negative. All right, any questions on that one? Okay, anyone still writing? Okay. Okay. Now, most proofs, I would say you don't have to worry about it. Just ignore it. But with these, the proofs are important only because in Calc 2, the process of finding these derivatives, you will have to kind of know to solve some problems in Calc 2. So with this one, the proof is kind of important. So we'll just prove one of them because they're all kind of similar. So we have the derivative of sine inverse of x is equal to 1 over the square root of 1 minus x squared. So we're going to prove this one. So what if we let y equal our sine inverse of x? Okay. So with any other function, if we apply the function and the inverse, they cancel each other out, leaving just the argument. So in this case, we're just going to apply sine to both sides. So that gives us sine of y is equal to sine of sine inverse of x. Where the sine and the sine inverse cancel each other out. So we know that sine of y is equal to x. Okay, so we can say that sine of y is equal to x, or we can say that sine of y is equal to x over 1. Okay, and we put it that way because now we know that sine of y is equal to the opposite over the hypotenuse. Your SO in SOHCAHTOA. So now we can create our right triangle. that we will need to solve the rest of this. So if we have our right triangle, let's say this is our angle that we will call theta. We know that our opposite is x. And our hypotenuse is 1. So if we use the Pythagorean theorem, we can solve for our adjacent, which is the square root of 1 minus x squared. Okay, so we were able to come up with this triangle knowing our sine of y. Okay. So again, we know that x is equal to sine of y. We're just going to differentiate both sides. We'll find the derivative. So we have the derivative of x with respect to x is equal to the derivative of sine of y with respect to x. Well, we know the derivative of x is just 1. So we can replace that with 1. Now with this one, you notice the two independent variables are different. So we want to differentiate sine of y with respect to x. We use the chain rule where the derivative of sine is cosine. So we have cosine of y. And make that O a little bit neater. Times the derivative of what's inside. So the derivative of x with respect to x of y. Okay, so we have 1 is equal to cosine of y times the derivative of y with respect to x. Okay, but we want to get that dy dx by itself. And actually, we could have left it in this form if we wanted to. But if we divide both sides by cosine of y, these two, anything divided by itself is equal to 1. So those two cancel each other out. Okay, so we have 1 divided by cosine is equal to the derivative of y with respect to x. And I'm just going to flip it around for my own little quirk. So derivative with respect to x of y is equal to 1 over cosine of y. Well, if you remember right from the top, we know that y is equal to sine inverse of x. So we can just take that, and we know that y is equal to sine inverse of x. So the derivative with respect to x of sine inverse of x is equal to 1 over cosine of y. Okay, well, we know that cosine is adjacent over hypotenuse. probably to make this less confusing, I probably should have let theta equal sine inverse, but too late now. Okay. Well, we have cosine is adjacent over hypotenuse. I'll just change that to y. Again, just to make it a little less confusing. There we go. Okay. So here, if we have the adjacent over the hypotenuse, that's just the square root. Make that a little bit lower. 1 over the square root of 1 minus x squared over 1, which you don't really need the over 1, but we'll put it there anyway. Which is just 1 over the square root of 1 minus x squared. Okay. So again, you don't have to kind of be able to follow this, we'll bring that over, fully here, but this process will be necessary in certain parts of Calc 2. All right, anyone still writing? All right, leave it up for a few more seconds. All right. So let's say, for example, if we wanted to find the derivative of r with respect to x, for r of x is equal to arc cosine of x to the 10th power. Okay. Now with this is just a notation change, that's all. If you have sine inverse of x, they sometimes call that arc sine of x. You have cosine inverse of x, they sometimes call it arc cosine of x. Same with tangent inverse of x. They call it arctangent of x. Secant inverse of x is arcsecant. Cosecant inverse of x is arccosecant. And cotangent inverse of x is arccotangent. So this is an arc cosine problem, so we know we're going to use this one. Okay. So we know that our r prime of x is just the derivative of arc cosine of x to the 10th power. Okay. So for this one, we're going to use the chain rule. So used to f of x. R prime of x is equal to, with the chain rule, we do the power rule by bringing down the 10 times arc cosine of x to the 10 minus 1 power. So go ahead and subtract 1 from that one. Times the derivative of what's inside. So that's the derivative of arc cosine of x. Now remember, arc cosine is just cosine inverse. So for this part right here, we just need to know that the derivative cosine inverse of x, and I want to squeeze it in there, but we know that's equal to -1 over the square root of 1 minus x squared. Okay, so our r prime of x is equal to 10 times arc cosine of x to the 9th power times the derivative of arc cosine, which is -1 over the square root of 1 minus x squared. So all we did was replace this one. So if you want to simplify this one, you can, even though I'm pretty sure Newton should take this with no problem. So r prime of x is equal to negative, and I'm just going to move the 10 and the arc cosine of x to the 9th power to the numerator. Divided by the square root of 1 minus x squared. All right. Are there any questions on this one? All right. Anyone still writing? All right. So let's say that if h of x is equal to x to the 9th power times arc cotangent of x. We want to find, I'm so used to f of x, h prime of x. Okay. Now with this one, just going to rewrite this so I can leave the original alone. Okay. Once again, notice that you have two functions being multiplied. And you're looking for the derivative. Okay. So in this case, we're going to use the product rule. for derivatives. So using the product rule, we have the first function times the derivative of the second function. So x to the 9th power times the derivative of arc cotangent of x plus the second function, arc cotangent of x, times the derivative of the first function. So that means our h prime of x is equal to x to the 9th power. And I'll put a little multiplication dot right there. Times the derivative of cotangent inverse, which is just the derivative of, if you want to put arc cotangent or cotangent inverse, is negative 1 over 1 plus x squared. Plus arc cotangent of x times the derivative of x to the 9th power, using the power rule for derivatives. That's 9x to the power of 9 minus 1, which is 8. Okay. So again, if you wanted to leave it like that, you could, or you could simplify this first term. So h prime of x is equal to negative x to the 9th power over 1 plus x squared. And with this one, it doesn't matter which one of these. You can make it plus 9x to the 8th power times arc cotangent. Make that a little clearer. Of x. All right. Are there any questions on that one? Okay. So what if, move that up a little bit. For example, we wanted to find h prime of x for h of x is equal to arctangent of x to the 5th power. Okay. So we know if we have anything other than just plain ordinary everyday x, then we know we're going to use that g of x formula. So remember that the derivative, you can say tangent inverse, but I'll just say arctangent of g of x, just to match it all up, is equal to g prime of x divided by 1 plus g of x squared. Okay. So for this one, our g of x is x to the 5th power. Which means our g prime of x is 5x to the 4th power. So we know that just plugging everything in, h prime of x is just the derivative of arctangent of x to the 5th power, which we know is g prime of x, which is 5x to the 4th power, divided by 1 plus g of x squared. So that's x to the 5th power squared. Okay. So if we simplify it, that gives us 5x to the 4th power over 1 plus x to the 10th power as our final answer. Oh, I had a paper clip up here. Nope, no paper clip. All right, any questions on that one? All right. Okay, so we're going to go ahead and start on section 3.8. Oh, anyone still writing? All right. Okay, so section 3.8, we will cover implicit differentiation. So let's say if we go back and we look at something like y is equal to 3x squared plus 2. Or you can rewrite that, since y is equal to f of x, you can also say f of x is equal to 3x squared plus 2. Okay. So we could see here that y is written explicitly as a function of x. Written as a function of x. Okay. Same thing if you had something like y equals 3 divided by x. Again, this is explicitly written as a function of x. But what if you had one where you had 3x squared plus 2y to the 3rd power plus 7x y is equal to 5? Okay. Now this one you can't really solve for x and y very easily. You can, but it'll be a very complicated looking problem. Okay. So in this form is written implicitly as a function of several variables. Well, in this case, two, but more than one variable. So it's written implicitly as a function of several variables. Okay. Again, you could just say two variables, but it applies to anything more than one. Okay. So even though our implicit equation is a jumbled mess of x and y variables all crammed in there, we can still find the derivative of it. And these are the guidelines to implicit differentiation. Oops. Again, these are just guidelines. If you have a method that you learned somewhere else that does not violate any laws of math and you want to use that one, you're more than welcome. Okay. So the first thing you're going to do, you're going to take the derivative of all the terms. So differentiate all terms on both sides of the equal sign. With respect to the independent variable. And that's usually x, but sometimes they will try to mix it up and throw a different one in there. But it is usually x. Okay. Now the thing is, for this step, for some of the terms, you will have to use the chain rule. And you'll immediately see which terms you'd have to use the chain rule for once you see the examples done a few times. Okay. So next, we want to collect all of the dy dx terms to one side and the non-dy dx terms to the other. Clean that y up a little. And that's just assuming that your independent variable is x. Terms to one side of the equal sign. And the remaining terms to the other. Okay, the reason you do that is for the third step, where you're going to factor out that dy dx. And solve. Going to do that. All right, anyone still writing? All right. Okay. So think about, in this case, how we will use the chain rule. Okay. So let's say, for example, we had the derivative with respect to x of x to the fifth power plus 9x to the fourth power. But we know, using the chain rule, we just apply the power rule to the whole thing. So that's 4 times x to the fifth power plus 9x to the 4 minus 1 power. So we say to the third power, times the derivative of what's inside, x to the fifth power plus 9x. So that's the chain rule when your independent variables both match up. These are all x terms, and you're differentiating with respect to x. Now let's say, instead of x to the fifth power plus 9x to the fourth power, we want to take the derivative with respect to x of y to the fourth power. Okay, but you can see here that your independent variables are not the same. But we do the exact same process. We take the power rule to the whole thing. So 4 times y to the 4 minus 1 power times, just like up here, the derivative of what's inside. So we take the derivative of what's inside of there, which is the derivative with respect to x of y. So it's the exact same process. The only difference is we're replacing this function of x with y. So we know our derivative of y, derivative with respect to x of y to the fourth power is just 4y to the third power times dy dx. All we did was rewrite that one. So this is how we're going to use our implicit differentiation. The exact same idea, just a little tweak to it. right. So let's say, for example, we wanted to find the derivative of y with respect to x, where y is defined implicitly as a function, I'll put it underneath here, x to the 9th power plus y to the 8th power is equal to 6. Okay. Now your denominator here and your dy dx will tell you with respect to what independent variable, but in this case it's x. So if you had dy dt, you differentiate with respect to t. So the first thing we're going to do, step number 1, oh, got my little solve there, is we're going to differentiate all terms with respect to x. Should have probably written that a little bit lower, a little closer to the question than I'd like. So that means we're just going to take the derivative with respect to x of x to the 9th power plus the derivative with respect to x of y to the 8th power equals the derivative with respect to x of 6. Okay. So you can see here, our independent variables are the same. So that means we can just use the regular ordinary power rule. So that's 9x to the power of 9 minus 1, which is to the 8th power. Plus, if you notice here, these two are not the same. You have the independent variable x differentiating with respect to the independent variable y. So any term where there's not the same, you're going to use the chain rule. So again, sometimes it helps if you put that y in parentheses. You don't have to. But we're going to use the power rule on the whole thing. So that's 8y to the power of 8 minus 1, which is 7, times the derivative of what's inside. So that's derivative of y with respect to x is equal to the derivative of a constant is always going to be 0. Okay, which brings us to our second step. We're going to put all dy dx terms to one side. And everything else on the other side. That means that 9x to the 8th power plus 8y to the 7th power times dy dx is equal to 0. This 8y to the 7th power times dy dx, that's one term, which means we have to get rid of this 9x to the 8th power. So we just subtract 9x to the 8th power from both sides. Uh-oh. these two cancel each other out. So we have 8y to the 7th power times dy dx is equal to negative 9x to the 8th power. Which brings us to our last step. Since there's only one term, you don't have to factor out a dy dx. So here, we can just solve. So that 8y to the 7th power times dy dx is equal to negative 9x to the 8th power. We're just going to divide both sides by 8y to the 7th power. Where these two cancel each other out. So we know our derivative of y with respect to x is equal to negative 9x to the 8th power divided by 8y to the 7th power. All right. Any questions on that one? All right. Okay, anyone still writing? All right. Okay, so let's say, for example, if we wanted to find your dy dx where y is a function of x implicitly for x squared minus x minus 2 equals 2y squared minus 24. Or let's say 2y. I don't know why I said 24. I think because my writing made this look like a 24. So again, the first step is you're going to take the derivative of each term with respect to x. So we have the derivative with respect to x of x squared minus the derivative with respect to x of x minus the derivative with respect to x of 2 is equal to, we can factor out that 2 right there, times the derivative with respect to x of y squared minus 2 times the derivative with respect to x of y. Okay. So again, if you go through, you can see that these two independent variables are the same. These two are the same. Well, that's a constant, so you know that's going to be 0. These are not the same. And these two are not the same. So the ones that are not the same, you already know you're going to use the chain rule for those. And same thing here. I'll just say use CR. Since I kind of ran out of room. Now, the ones where they're the same, you just differentiate like we've been doing this whole time. So the derivative of x squared with respect to x is 2x minus the derivative of x with respect to x is just 1 minus the derivative of a constant is 0, so that just disappears, is equal to 2 times the derivative with respect to x of y squared using the chain rule. So that's going to be 2 times y to the power of 2 minus 1, which is just 1, which you don't have to put the 1 there if you don't want to, times, and again, if you put the parentheses around there, it's the derivative of what's inside, the derivative of y with respect to x. Okay, so this whole derivative is represented by that. Okay, minus 2 times the derivative with respect to x of y is our derivative of y. Well, you could say y to the power of 1, which is just y to the power of 1 minus 1, which is 0. So this just becomes 1. So whenever you see the derivative with respect to x of just y, you can just rewrite that as dy dx. Because using the chain rule, it'll just become dy dx times 1. Actually, let me write out the whole step. I just would feel better knowing you can see the whole step. But it's going to give you the same dy dx. It's just I'm going to write out the whole process. Okay, so instead of y, we'll change that to y to the first power. So again, if we bring down the 1 times y to the power of 1 minus 1 times the derivative with respect to x of y. Okay, so again, that's just times what's inside, the derivative of what's inside. So again, y to the 0 power is just 1. 1 times 1 is 1. 1 times dy dx is just dy dx. So that's why I just made this dy dx. So when it's just y by itself, you can kind of skip all of that if you want to. Just make it dy dx. Now, if it's y to the power of something other than 1, then you have to go through the whole process. But if it's just y by itself, just make it dy dx. So we have 2x minus 1 is equal to, we can go ahead and multiply those two. So 2 times 2 is 4 times y times dy dx minus, and again, if we want, we can go ahead and multiply those two. 2 times 1 is just 2, so that was no big deal. Times y to the power of 0, which is 1, times dy dx. Okay. Now with this one, we can skip the second step because your dy dx, they're both already on one side. Okay, so we can kind of skip that step. brings us right to the third step, where we factor out dy dx and solve. So that 2x minus 1 is equal to, and if we factor out dy dx, that's just 4y minus 2 times dy dx. Okay, so to solve it, all we have to do is divide both sides by 4y minus 2. So 2x minus 1 is equal to 4y minus 2 times dy dx. Divide this side by 4y minus 2, and this side by 4y minus 2. Okay, so anything divided by itself is always going to be 1, so those two cancel each other out. So we have 2x minus 1 divided by 4y minus 2 is equal to our dy dx. All right, any questions on that one? All right, anyone still writing? All right. Excuse me. Okay, let's say, for example, if we wanted to find the second derivative. Where y is defined implicitly by negative 3x to the fourth power plus y to the fourth power is equal to 4. Okay, so just like before, your very first step is you're going to differentiate each term. So that gives us negative 3 times the derivative with respect to x of x to the fourth power plus the derivative with respect to x of y to the fourth power is equal to the derivative with respect to x of 4. Okay, so again, we can see here these two, the same independent variables, so we differentiate those like we normally would. These are not the same, so we know we're going to use the chain rule. And that's derivative of a constant, that's just going to disappear. So we know this one's going to be -3 times the derivative of x to the fourth power, which is 4x to the 4 minus 1 power, which is to the third, plus, using the chain rule, again, I'll put a little parentheses around the y. We take the power rule of the whole thing. So it's 4y to the power of 4 minus 1 times the derivative of what's inside, which is y. So the derivative of y with respect to x is equal to the derivative of a constant is just 0. Okay, so we go to our second step where we isolate our dy dx terms. So if we go ahead and multiply those two, we get -12x to the third power plus 4y to the third power times dy dx is equal to 0. Which means if we want to get this term by itself, we have to add 12x to the third power to both sides. These two cancel out. Which leaves us with 4y to the third power times dy dx is equal to 12x to the third power. Which brings us to our third step where we divide and solve for dy dx. That 4y to the third power times dy dx equals 12x to the third power. We're just going to divide both sides by 4y to the third power. And we know that anything divided by itself is just 1, so those two cancel each other out. So we know our dy dx is equal to 12x to the third power divided by 4y to the third power. Or we could rewrite that as the derivative with respect to x of y is equal to 12 divided by 4 is 3. So it's 3x to the third power divided by y to the third power. And there's a reason I wrote it this way, and we'll see that on the next page. So now we found the first derivative. Now we have to use the derivative of the first derivative to find the second derivative. All right, anyone still writing? All right. Okay, now our second derivative is just the derivative of our first derivative. Okay, so here we're trying to find the derivative of a quotient, which means we have to use the quotient rule. Okay, so we know our second derivative with respect to x is equal to your denominator times the derivative of your numerator minus your numerator times the derivative of your denominator, all divided by your denominator squared. So y to the third power squared. Okay, so we have our y to the third power times the derivative of 3 times x to the third power with respect to x. So using the power rule, we bring down the 3. So 3 times 3 is 9 times x to the power of 3 minus 1, which is 2. Minus 3x to the third power times the derivative with respect to x of y to the third power. Okay, so using the chain rule, we have 3y squared times the derivative of y with respect to x, or the derivative with respect to x of your y. All divided by y to the third power squared is y to the sixth power. Okay. Now with this one, you just have to see that and remember that the derivative with respect to x of y is 3x to the third power over y to the third power. So we can actually rewrite this. And this one, we can just call this 9x squared times y to the third. Since we know that multiplication is commutative, we can just shuffle those right on around. Minus 3 times x to the third power, and we could have multiplied those here, but I'll do that in the next step. Times 3y squared, and that derivative of y with respect to x, my Monday morning tongue, we can replace that with 3x to the third power divided by y to the third power. And all of that divided by y to the sixth power. And make that 6 a little neater. Okay. So here we can actually, because all of these are just being multiplied to each other. So we can multiply the 3, this 3, and this 3. So that gives us 9x squared times y to the third power minus 27 if we multiply those 3 3's together. And this x and this x term or factor, we have x to the third times x to the third. It gives us x to the sixth power. we take this y squared times 1 over y to the third power, that gives us 1 over y. Divided by y to the sixth power. Now with Newton, they may or may not accept this form. But it's an easy way to fix it in a form to where they will accept it. We just have to get rid of that 1 over y. So we just multiply the numerator and denominator by y. Which means we're multiplying this whole thing by y. So from there, we're just going to go ahead and distribute the y to both of these terms. So that gives us 9x squared times y to the fourth power minus 27x to the sixth power. This y and this y cancel each other out, so that just becomes 1. All divided by, we multiply these two, that just gives us y to the seventh power. And another problem with this form is that you're going to be using a ton of parentheses to type it in, which is you're just leaving one off to an incorrect problem. Sometimes it's just easier to simplify it. So they may take it in this form, but like I said, with all those parentheses, it's just a mistake waiting to happen. So sometimes it's best to put it in the simplest form you can. All right, any questions on that one? All right. Okay, anyone still writing? All right. Let's get off of there. There we go. So what if we want to find the equation of the tangent line? At the point -3, 2 to the implicit curve -4x squared plus 3y squared is equal to -24. So if you remember, whenever you see a question that asks for the equation of the tangent line, that means you're going to use some form of the point slope formula. So y minus y1 is equal to the slope times x minus x1. Now the slope of the tangent line is just the first derivative. And in this case, that first derivative is dy dx at the point -3, 2. Okay, and just a heads up that if you happen to see a different notation, it's the same thing. So if you see the derivative of y with respect to x at -3, 2, make that a little lower. Sometimes they will write it as the derivative of y with respect to x, and then they'll put like a little line and say -3, 2. So if you see that notation, that's all it means. Okay, so first thing we have to do is find our dy dx. So we take the derivative of each term. So the derivative, let me factor out that -4 first, just to get that out of the way. So we have -4 times the derivative with respect to x of x squared, plus 3 times the derivative with respect to x of y squared, equals the derivative with respect to x of -24, which we already know that's just going to be 0. Derivative of a constant is always 0. So that gives us -4 times the derivative of x squared. Again, the two independent variables are the same. So we just use the power rule, which gives us 2x. Plus 3 times the derivative of y squared with respect to x. Again, the independent variables are different, so we know we're going to use the chain rule. So that's going to be 2y times the derivative of what's inside. Remember, that's to the power of 2 minus 1. Let me write that just to your derivative of y with respect to x is equal to 0. And I might as well write to the power of 2 minus 1 here also, just to stay consistent. So if we go ahead and multiply these two, that gives us -8 times x to the power of 2 minus 1, which is just x. And if we multiply these two, 3 times 2 gives us 6 times y to the power of 2 minus 1, which is just y, times dy dx is equal to 0. Okay, so remember, now we have to isolate our dy dx term. So we have -8x, so we have to add 8x to both sides. Where those two cancel each other out. So that gives us 6y times dy dx is equal to 8x. So if we divide both sides by 6y, those two cancel each other out. So we know that dy dx is equal to 8x divided by 6y. Or we can actually simplify this. Just say our dy dx, we divide both of those by 2, is equal to 4x divided by 3y. Now remember, this is your slope of the tangent line. So now we need the slope of the tangent line at the point negative 3, 2. So your slope of the tangent line at negative 3, 2, that's just your dy dx at the point negative 3, 2. Which is 4 times negative 3. We just plug in our x and y, divided by 3 times negative 2, 3 times 2. That's just your x, and that's your y. That gives us negative 12 over 6, which is just negative 2. So we know that our slope of the tangent line at the point negative 3, 2 is negative 2. And we can use that to finish it up on the next page. All right, anyone still writing? Okay. Okay, so we know the slope of the tangent line is negative 2, and that's at the point negative 3, 2. And we know we're looking for the equation of the tangent line, so we know we're going to use y minus y1 is equal to the slope times x minus x1. Okay. What we know here, we have our x1 and y1. So our y minus y1 is y minus 2. Is equal to the slope of the tangent line, which is negative 2, times x minus x number 1, or x minus negative 3. Or we can just rewrite it as y minus 2 is equal to negative 2 times x plus 3. So if we distribute that negative 2, it gives us y minus 2 is equal to negative 2x minus 6. And if we add 2 to both sides, it gives us y is equal to negative 2x minus 4. Okay, so that's our tangent line equation. At the point -3, 2. Okay, so if you graph your original function, and you want to know exactly where the tangent line or what the tangent line would look like at that point, then you just have that one. All right, any questions on that one? All right, anyone still writing? Okay. Now, what if we wanted to find dy dx for sine of xy is equal to 6x to the third power times y squared plus 3. Okay. So with this one, it might get a little bit lengthy. Okay, so remember your first step. Take the derivative of each term. So the derivative, again, we know we're looking for the derivative with respect to x. Sine of x times y is equal to 6 times the derivative of x to the third power times y squared plus the derivative with respect to x of 3, which we already know is just going to be 0, since the derivative of a constant is always 0. Okay. So again, here we know we're going to end up needing the chain rule. And same thing here. Not only do we need the chain rule, we need the product rule and the chain rule. But first, we're going to need the product rule because we're multiplying two functions. And we're looking for that derivative. Okay. So using the chain rule for trig functions, we know the derivative of sine of xy, derivative of sine is cosine. That gives us cosine of x times y times the derivative of what's inside. So that's the derivative of x times y. And I'll just do the product rule for both at the same time. So I'll just rewrite this one the way it is. So 6 times the derivative with respect to x of x to the third power y squared. And that's just 0, so that disappears. So again, we know we're going to need the product rule for both of these. So this one, we know we're going to use the product rule. And for these two, for the derivative, we know we're going to need the product rule. Okay, so we have cosine of x times y. And using the product rule, you have the first function times the derivative of the second. So x times the derivative with respect to x of y plus the second function, which is y, times the derivative of the first, times the derivative with respect to x of x. Okay, and that's equal to 6 times, using the product rule again, you have the first function, which is x to the third power, times the derivative with respect to x of your second function, which is y squared, plus the second function times the derivative with respect to x of the first function, which is x to the third power. Okay, so if we simplify each one of those one by one, we get cosine of x times y times, you have x times dy dx, so we can just combine those two. So x times dy dx plus y times the derivative of x with respect to x is just 1. Is equal to 6. And again, we just simplify all of this. So we have x to the third power times the derivative of y squared with respect to x. So again, we're going to have to use the chain rule or implicit differentiation, which is just a version of the chain rule. So that's 2 times y times the derivative of what's inside, which is the derivative of y with respect to x. Plus y squared times the derivative of x to the third power with respect to x. Okay. Same independent variable, so we just use the power rule, which gives us 3x squared times 3x squared. Okay. So we know we have to get our dy dx terms by themselves. We have to get them on one side so we can factor them out. So we're going to go ahead and distribute that cosine of xy to both of these terms. And we're going to distribute the 6 to both of these terms. Okay, so we have cosine of xy times x times dy dx. And again, it doesn't matter what order you put them in. So I'll just say x times cosine of xy times dy dx. Plus, well, y times 1 is just y. So we have y times cosine of xy. Make this y a little bit neater. Here we go. Okay. So we distribute the 6 here. We can multiply that 6 times 2, which is 12. So that's equal to 12 times x to the third power times y times dy dx. And if we distribute this 6, we can multiply it by the 3 that's already there. So that's 6 times 3 is 18. So that's plus 18 times x squared times y squared. So that brings us to our second step, is we have to get all the dy dx terms to one side and all the terms that don't have dy dx to the other. So we're going to move this term over to the left, and this y times cosine of xy, we're going to move that over to the right. And I'll just rewrite it out. So x times cosine of xy times dy dx plus y times cosine of xy is equal to 12x to the third power y dy dx plus 18x squared y squared. So I'm just going to subtract 12x to the third power times y times dy dx on both sides of the equal sign. We know these two cancel each other out and become 0. Then we're going to subtract y times cosine of xy on both sides. Where these two cancel out and become 0. So that gives us all of our dy dx terms on one side. So we have x times cosine of xy times dy dx minus 12 times x to the third power times y times dy dx is equal to 18x squared y squared minus y times cosine of xy. Which brings us to our third step. You just have to factor out our dy dx. And solve. Okay, so that gives us dy dx, if we factor out of both of those terms, times x times cosine of x times y minus 12x to the third power times y is equal to 18x squared. Make that a little bit lower. 18x squared y squared minus y times cosine of x times y. So now all we have to do is divide both sides by x times cosine of xy minus 12x to the third times y. X times cosine of x times y minus 12 times x to the third power times y. And this side by x times cosine of xy minus 12 times x to the third power times y. Where anything divided by itself is just equal to 1. So those two cancel each other out. Those whole things. So finally, we know that our dy dx is equal to 18x squared y squared minus y times cosine of xy divided by x times cosine of xy minus 12x to the third times y. So again, problems like this can be a little bit tricky, so you want to be careful with these. All right, are there any questions on this one? Any steps that didn't make sense? All right. Okay. Scan likely again. All right, anyone still writing? Okay. Okay, so now we're going to start on section 3.9. Which covers the derivative of exponential and logarithmic functions. And most of these are just plugging in values. So if you know the formula, you just plug those in and you're all done. Okay, so probably the easiest one to remember is the derivative with respect to x of e to the power of x. It's just e to the power of x. And if we have the derivative instead of e to the power of x, what if you had e to the power of x squared plus 5 or something like that? Or any function that we will call g of x. Well, that's just equal to e to the power of g of x times the derivative of that exponent. So times g prime of x. So we'll look at the proof of the first one. The second one is not that far off from it, so we'll only prove the first one. Okay. So we have the derivative, we'll say the proof of 1, with respect to x of e to the power of x. And there are multiple proofs that you could use for this one. This is just one of them. So if you see a different one online, they're correct also. It's just multiple ways to prove this one. Okay, well, we know that this is just the limit as h approaches 0 of f of x plus h. So replace x with x plus h, so that gives us e to the power of x plus h, minus f of x, which is your e to the power of x, all divided by h. Okay. Well, the same way, if we had x to the third power times x to the fifth power is equal to x to the power of 3 plus 5, we can rewrite e to the power of x plus h as e to the power of x times e to the power of h. So the limit as h approaches 0 of e to the power of x times e to the power of h minus e to the power of x all over h. Okay, so we can see here we can factor in e to the power of x out of both of those. So that gives us the limit as h approaches 0 of e to the power of x times e to the power of h minus 1 all over h. Okay, so we know that from our limit definition, our limit properties, we can apply the limit to both of those. So that's just the limit as h approaches 0 of e to the power of x times the limit as h approaches 0 of e to the power of h minus 1 all over h. Okay, so if we plug in various values for h getting closer and closer and closer to 0, we can see that this limit is just equal to 1. So that's the limit as h approaches 0 of e to the power of x times 1, which is just the limit of e to the power of x. Okay. So if we try direct substitution, there are no h's that we can replace with 0. So the limit of e to the power of x as h approaches 0 is just e to the power of x times 1, which is e to the power of x. All right. So let's say, for example, so let's say for f of x is equal to 2 times e to the power of x, I want to find f prime of x. Okay. So for this one, we know that f prime of x is just 2 times the derivative of e to the power of x. Which means that our f prime of x is equal to 2, and the derivative of e to the power of x is just e to the power of x. Or you can just rewrite it as 2e to the power of x. Which is why that one's the easiest derivative to remember. It's just the same thing. Okay. Now, one trick question that I don't want you to fall for, so I'm going to show you why you shouldn't fall for it. So let's say we have f of x is equal to e to the 7th power. And we want to find f prime of x. Well, f prime of x is just the derivative of e to the 7th power. Which is 0. And the reason e is a number, because remember that e is just approximately equal to 2.71828, and it keeps on going and going and going. So it's no different than saying the derivative of 5 to the 7th power. And we know the derivative of a constant is always going to be 0. So first instinct would be to make that e to the 7th power. So you don't want to do that because remember, that's with respect to x, and that's just a constant. Or what if we wanted to find the derivative for f of x is equal to e to the power of x squared? We want to find our f prime of x. Okay. So remember, if that exponent is anything other than x, just plain ordinary by itself x, you want to remember that the derivative of e to the power of some function g of x is equal to e to the power of g of x times the derivative of that g of x. Actually, I'll just put g prime of x. Which is also true for e to the power of x, because that's just e to the power of x times the derivative of x, which is just 1. But if it's something other than x, you can't just say the derivative is e to the power of x squared, because it wouldn't be correct. So our f prime of x is just the derivative of e to the power of x squared. Remember, in this case, your x squared is equal to g of x. So that means it's going to be equal to e to the power of x squared times the derivative of that x squared. Remember, that's just your e to the power of g of x, and that's your g prime of x. So that's just e to the power of x squared times the derivative of x squared, which is 2x. So if you wanted to, you could just rewrite it as your f prime of x is equal to, you can bring the 2x out to the front, doesn't matter, or you can leave it like that. I'll just say 2x e to the power of x squared. Both forms are correct, but that one's just a little bit neater. No need for parentheses or anything like that. All right, any questions on that one? All right, anyone still writing? Okay. Okay, so what if we wanted to find h prime of x if h of x is equal to x to the negative 7th power plus e to the negative 8x power? So again, we know that our h prime of x is just the derivative of each term. So we take the derivative with respect to x of x to the negative 7th power plus the derivative with respect to x of e to the power of negative 8x. Okay, which means that our h prime of x is equal to the derivative of x to the negative 7th power using the power rule. Bring down the negative 7 times x to the power of negative 7 minus 1 plus the derivative of e to the power of g of x is equal to e to the power of that g of x, which is negative 8x, times the derivative of negative 8x. So your h prime of x is going to equal negative 7 times x to the power of negative 8. And that negative 8x, we can go ahead and move that out to the front. I mean, that negative 8, rather. Actually, let me not skip a step. So e to the power of negative 8x times the derivative of negative 8x, which is negative 8. So at negative 8, we can go ahead and move out to the front. So h prime of x is equal to negative 7x to the negative 8th power minus 8 times e to the power of negative 8x. Okay. Again, remember, sometimes Newton may be a little bit tricky about those negative exponents in the answer. So if you wanted to, or if you had to, you could rewrite it. That x to the power of negative 8, move it to the denominator and make it positive. So that's negative 7 over x to the power of 8. Minus, same thing with negative e to the power of negative 8x. You make that 8 over e to the power of 8x. Okay. Again, both are correct, but Newton might prefer it in one form over the other. Okay, so I'll go ahead and stop there only because I know this next example is going to take longer than 8 minutes. That's how much time we have left. All right. So if you have questions, of course, hang back, ask away. If not, I will see you tomorrow. Let me see.
Hi. I was the one who messaged you about the exam not working for me.
Yeah.
I was just wondering, is it like worst case scenario, I just have to take a 0 for it, or?
Well, normally at the end of the semester, what I do is I'll kind of reopen all of the exams. It's mostly just for the people who may have missed it.
Sure.
So with that one, because it was started, it wasn't technically missed.
Oh, it
So-
just didn't like load. It
Yeah.
was a wrong.
Yep. So with
So for
that
that
one,
do you think like?
it was reset, so you should have been able to take it.
Oh, I
Did
don't think it.
It should have reset.
So like I got it to open,
Mhm.
but only like the first question would load, and the rest of it didn't load. And then I borrowed a computer later after I saw your message, and I got it to work, but like it only let me in for like a second because it timed out.
Oh, okay.
Because I didn't actually get to see any questions or input it.
Mhm.
So do you want to like think about it and then like let me know what my options would
Let me
be?
see. With that one, let me make a note.
Yeah, you can just let me know like
Yep.
later.
And I can take a look at it.
I understand it's my fault, but I was like really trying to get it to work and it was not cooperating.
Okay, so I'll make a note of that. And after I'll take a look and see like how far you got into it.
I
just
wasn't
to
even
make sure.
able to like input anything. But,
All right, I'll let you know.
all right, thank you.
You're welcome. Hello.
Is there anything else I need to know for the past 2 weeks?
Uh,
Other than the lectures or